All right, energy is a very important, almost worldwide topic for how are we going to get power for the things that we use every day. How do we go from point A to point B? How do we keep our houses warm or cool? How do we, how am I even using this laptop to record this video lecture? It's all dependent on the energy and how we use it. So we're going to talk about fossil fuels, nuclear energy, and renewable energy. We'll talk about the problems, advantages, and disadvantages of each. And in class, we'll have some more applied discussion on these different types of energy. We're going to start with fossil fuels. So the first fossil fuel to really be used wide scale was coal, which during the Industrial Revolution was used to provide energy to to heat up water to make steam-powered engines, which powered everything from locomotives to factories. Oil, which was used widespread throughout the U.S. and then the world with the advent of the internal combustion engine. And finally, gas, which is mostly methane, so we're talking about natural gas. And this is found when exploring or drilling for oil and can also be used and burned to create electricity or power transportation. Now, the use of energy is continually changing. Coal, oil, natural gas, this is the large percentage of U.S. energy use. And however, it has shown shifts even in the past few years. So natural gas has increased in its use, oil has slightly decreased, and coal has slightly increased. This is in the global primary energy supply. And the idea is that these chunks of pie over here, which are our nuclear and renewable energy sources, there are efforts to make these much bigger and a much greater proportion of the overall energy we use, and phasing out these fossil fuels. So fossil fuels are also finite in their abundance throughout the world. The way that they formed was through photosynthetic organisms and non-photosynthetic organisms, over time accumulating debris and over millions of years creating these thick organic layers which are being decomposed by bacteria. But not all of it decomposes all at once. Eventually, some of this is trapped under sediments, and then through time, heat, and pressure over, again, millions of years, those will form these hydrocarbons, which form coal, oil, and natural gas. We have then started to drill, explore, and extract these from the earth and burn them, and they power our energy demands and transportation, electricity, and anything else we use energy for. The most usable form of energy is electrical power. And electrical power is the amount of work done by an electrical current over time, so we can convert it to mechanical energy, or we can use it for light bulbs, or for running your computer. To get electrical power, you have to have a carrier which transfers energy from a primary energy source to the point in which you want it to be used. So you have a power plant which supplies power into residential homes through power lines which conduct electricity. So those lines are the energy carriers. The generator then is the point at which at your power plant the energy is converted from one form to another. The electric generator, what it does is it converts mechanical energy into electrical energy. And the way that does that is if you move a wire through a magnetic field, it creates an electrical current. And that current is then used as, is electricity and is used for energy. A turbine is a sophisticated paddle wheel which can move this coil of wire through that magnetic field. So we can, the steam engine can turn a turbine. When you combine the turbine and the generator, you have a turbo generator, which then provides an electrical current. Now, energy use in the United States, so we showed the world pie chart earlier, is different than the world, right? So we use nuclear power in New England for a significant part of the grid or the electricity being used. But United States as a whole uses mostly coal, and the world as well. Oil and natural gas make up then about 60% of the U.S. and about 65% of the world. Now, throughout the day, this shows the cycle of energy use throughout the days of the week and throughout individual days. And this is something you have to consider when talking about energy use. Most energy is used in weekdays, so Monday, Tuesday, Wednesday, Thursday, Friday, during the daytime, because this is when everyone is at work and most electricity is being used. At night, everything is turned off generally. And then on the weekends, less work is being done, so less electricity is being used. So any sort of energy supplier has to take into account these fluctuations in energy demand. So when those things are not taken into account, then you can run into problems such as a reduction in voltage, where maybe it's pulling more electricity is being used than is able to be provided, at least in a sustainable manner, and so that may reduce the amount of electrical current or the amount of voltage being distributed. A blackout is when something occurs and you have complete loss of power. And we had a complete loss of power, I want to say close to 2003. So over 10 years ago, there was a blackout in the northeastern United States, which stretched from Ohio all the way over to New York and up into Pennsylvania. And it lasted a few days before they were able to get things back online. Pollution is also a problem. You can have this is a nuclear power plant which produces thermal pollution in the form of heat, but you can also have things that cause acid rain and other things. Efficiency is always a problem, so when you are converting energy from one form to another, it is not always 100% efficient. And so making things the most efficient is always a objective of energy providers. Burning fossil fuels is only 30 to 35% efficient, so 60 to 65% or 65 to 70% of all that energy is just lost as heat. Condensers are also another thing that are used to use this steam to try and conserve the water use and converting it back to water. Thermal pollution, as I mentioned, so when things have to be cooled down, generally water is used, and warm water is then pumped back into waterways, which isn't the natural state in which it started, and so it can affect a lot of organisms that live there. All right, this is a nice big graph which shows, again, the breakdown and the use of energy in the U.S. So we have a lot of different diversity of different types of energy providers which go into our grid for creating electricity, which we then use for powering laptops or commercial uses, and even some industrial uses as well. Petroleum is the biggest provider of transportation, and transportation is the biggest producer of carbon dioxide, which contributes to global warming. But as you can see, it is very diverse in the different sources, however, their use is largely on these coal, petroleum, natural gas areas. And we again are highlighting here a lot of this energy use results in a lot of wasted energy. We just can't get all of it into our to be useful for what we are doing. So on the front end of this, we have to have processes for pulling these resources out of the ground. And so oil extraction is something that is huge. It's a giant industry, probably one of the biggest in the world in extracting and refining oil. So when an area is being explored, it first has an estimation of the reserves, or how much oil is in the ground, and that can then be pulled out to be used. There are high cost operations where people go in, or companies go in and try and find oil, and when it is found and the reserves are estimated, and then they start to pull oil out of there, you have then an oil field. And then after you have your oil field, you can have a better estimation of how much oil is actually there. Once it's in use, you have production, where it's being removed. And this goes in 3 different stages. So primary recovery is the easiest. All you have to do is pump it out of the ground, and you can get 25% of the oil, no problem. After that, you have to inject something in there to get the rest of it out, so it'll stick to the rocks and the substrate and the things that it's down there with. So injection of brine or steam can help remove the next 50%. Okay, the last bit, the enhanced recovery, requires injecting carbon dioxide to break up the oil droplets and getting it all out even more. You can't get 100% of the oil, but you can get close to 80 or 90%. And maybe technology in the future will allow us to get all of it, but there's still some residue there that it just isn't worth the extra effort to get. So with the use and production of oil into forms which we can use for energy, you're going to have a very fluctuating price. So production paralleled increase in consumption leads to a stable price, and generally this is what once you first start using oil, first find an area, you're going to produce as much as you are using. But once it's used, once it's consumed more than you can produce, this results in you having to get oil from somewhere else, so you start having imports. And this is what has happened in the U.S. This is also going to cause an increase in the price. An increase in the price is going to decrease consumption. We've seen that a few times in recessions. And consumption then has increased, and production has declined, leaving the U.S. dependent on foreign oil. And so we do not produce as much as we consume, so we have to fill that gap. Imports and are dependent on foreign oil. Prices and adjustments to the prices affect the behavior of everyday people like you and me. So when oil prices are high, oil exploration is high as well, because you can gain a lot of profit from finding oil. The standards for automobile fuel efficiency usually increase because consumers want more fuel efficient vehicles, so they don't have to spend as much money. Oil reserves are opened up and used, and subsidies and tax incentives are given for renewable energy to try and wean off of these fossil fuels. However, when prices are low, these concerns aren't as urgent. So production decreases, you can't get as much profit, from low prices. The conservation incentives to use less oils are abandoned because the price is low, so people don't really care. And with that, those tax incentives and alternative energy subsidies are canceled. So this is a graph again showing that our consumption is much higher than production, and therefore our imports have increased, and we export some amount of oil, but not as much as we import. So the cost of purchasing oil is a drain on our economy, and also makes oil very fluctuating in its price. If even there is a threat of some sort of disruption in oil production, this can affect fuel prices, even if the actual supply is not affected. So any conflicts in the Middle East generally will cause a rippling effect on your gas prices. And ultimately, there's resource limitations. So there is only so much oil out there. It's not replenishing itself. It's not a sustainable resource. And this is very evidence of this is seen in what is called these Hubbert Curves. So after a country opens itself to oil exploration, it will increase production quite a bit until eventually you start to see this in pretty much every country. We've hit our peak and our max production, and we're now decreasing the amount of oil that we can pull from these reserves, from these oil fields. So other fossil fuels include natural gas, which is cheaper than gasoline. It's cleaner, meaning there isn't as much residue and pollutants when it's burned. And there's estimated there's about 50 years of this still remaining in oil fields. But it is hard to transport and liquefy because it is a gas. Coal, there's lots of coal. We have tons of it, but mining of it is very destructive. And it releases a lot of pollutants into the air. There's lots of it, so it's the least expensive. Oil shale and oil sands. So this is also, actually I think this is from an oil tar sand operation. Very destructive to the land. You have to actually pull the sand out and filter it out, and then you can use that for oil. So it's very expensive also to produce. So this is usually only done when oil prices are really high. So some of the policies focus on the supply side by increasing the supply of fossil fuels and decreasing the price, but it doesn't address the problems of pollution and the environmental degradation. So this is policies for oil or fossil fuels on the supply side are kind of the business as usual. Let's just make it as cheap as possible, use as much as we can, and we're starting to see this actually with some of Trump's new policies with coal. On the demand side, it focuses on reducing the use of fossil fuels by increasing efficiency and increasing the use of alternative energy sources or renewable energy sources. Okay, so that's it for fossil fuels. Now we're going to get into one of those alternative energy sources, nuclear power. Nuclear power had a big boom in the 70s and 60s. It takes a long time to make a plant and then put it in service. And there were a lot of proposed number of plants that never actually made it into operation. Right now in the US, we don't really have any more proposed. Maybe there's a couple new ones within the past few years. But generally, since the late 80s, early 90s, we've had about the same number of nuclear power plants in operation. So the way nuclear power plants work is they use these very large elements that are highly radioactive, that also are highly unstable, and that when they react, they give off a lot of energy. We use that energy to turn to power a turbo generator and provide electricity. Uranium, to get it to start, you have to bombard it with neutrons, and that causes it to split. And this is the fission reactors. Okay, this also, one of the products is neutrons, which will cause more uranium to split and cause more energy to be given off, so we can use that for electricity as well. Fusion is another type of reaction where you can take hydrogen, different isotopes of hydrogen, and make them come together, and then they will also release energy. However, this can only be done at very hot temperatures, so it's not very feasible. So what happens if you have some enriched uranium and you, again, bombard it with something and cause a reaction? If there's enough in there, it'll cause a chain reaction where you have all this splitting of uranium, or fission of uranium, and then it's giving off energy as it splits. Now, if you have enough in there, it'll cause a lot of uranium to split at the same time, and that is how an atom bomb is made. But what you want, so that'll be a self-amplifying chain reaction. What you want to power electrical grids, though, is a sustaining self-reaction where you have the reaction under control. It's not causing everything to explode, so you have to have something to absorb some of these particles to prevent a chain reaction. And so the way nuclear power plants work is they are generally in water, which will kind of help absorb the heat, and then you have some substance which will absorb some of these neutrons to prevent a chain reaction from occurring and everything exploding. So that's generally how it works on the molecular level. When you look at it compared to our fossil fuels, there's a lot of advantages to nuclear power. The fuel needed is very abundant, uranium, and does require mining, but not as much mining as other types of fossil fuels. The carbon dioxide emissions are much lower, and there are no sulfur dioxide emissions either. You're basically just using water, and water vapor is your only pollution other than the excess heat. However, you do have to deal with radioactivity, and so there's radioactive wastes, and those can cause a health hazard to workers, and if released into the water, to anyone using that water. So that must be dealt with very carefully. There's much less solid waste. There's lots of solid waste with fossil fuels. However, accidents. So accidents do occur with mining. We've had that highlighted in the news a few times with coal miners, and human health hazards are abundant in coal mining. But an accident is very localized and only affects a few people, whereas an accident at a nuclear power plant could cause a giant explosion, lots of radiation, and affect much more people. So that's kind of the cost-benefit analysis you have to run between those. So in nuclear power, you have different byproducts, including radioisotopes. These are unstable elements which become stable by emitting radioactive particles. Those radioactive particles are what can cause cancer and other health problems. Curies is a unit of measurement which will help you measure radioactivity. So you go into a power plant, you measure the radioactivity in curies and determine whether or not it's safe. Radioactive emissions include alpha particles, beta particles, X-rays, gamma rays, and neutrons. And so those are things that can be measured in curies. And finally, radioactive waste, we talked about that. So you have indirect products of fission that emit some of these radioactive particles or radioactive isotopes. Okay, so you have neutrons, you have these direct products of fission, which are radioisotopes, which are going to give off these emissions over time. Eventually, after those radioactive emissions have been getting off, you'll have a stable isotope, which is just fine. It's not going to hurt anyone. But you need to take into account radioisotopes, radioactive radiations, and these byproducts when you have a nuclear power plant. So the effects then of these in low doses over many over long exposure times can cause cancer, can cause cataracts in the eye, can kill white blood cells and cause immune deficiencies, can have nervous damage, damage to DNA, all these things can occur. In high dose, so if you were, let's say, near an atom bomb explosion or during the nuclear accident in Fukushima, the Daiichi power plant, you can have a lot of very acute damage to your tissues, and it can cause leukemia, death to blood cells, neurological damage, and death. And these may not be present right away. They can manifest themselves later in life as cancer and other things. So one of the big problems then with nuclear power is, what do we do with the waste? So there is some which doesn't have a big problem with short-term containment, which only needs 10 years storage for their radioactivity to mostly be dissipated. But a long-term containment, so the EPA requires that you have a 10,000 year minimum storage of some of the long-lived isotopes, which is longer than anyone is going to live. So what are you going to do with this stuff for 10,000 years? Now, one of the solutions is to bury it in these deserted wastelands, such as in Yucca Mountain in Nevada, I believe. However, Nevadans don't really want a bunch of radioactive material in their backyard, so there's a lot of controversy as to where we're going to put this, who's it going to affect, and social considerations with that. Another big negative is, what if something goes wrong? So what about accidents? So there was an accident, was mostly contained in 3 Mile Island nuclear power plant in Harrisburg, Pennsylvania in 1979. After this accident, there was a lot of skepticism as to whether or not nuclear power should be as abundant as it was, and so a lot less were a lot of plans for nuclear power plants were canceled. In addition to that, in 1986 in USSR, there was a meltdown in Chernobyl, and the whole area around Chernobyl had to be evacuated and is inhospitable. People still don't live there. And then more recently, the Fukushima Daiichi power plant, where an earthquake and tsunami damaged the power plant, which then led to an inability to cool the reactors and caused a meltdown. So this is a place where it was also evacuated. There are some workers allowed in there which do work on the containment, but it's going to take up to 50 years to fully contain. So accidents are very costly and have widespread effects, and so there need to be a lot of safety protocols in place to make sure that these don't happen. So again, some positives and negatives. Nuclear power is clean, it's renewable, it's inexpensive once the plant is made, so it's inexpensive to contain. It's very efficient, and it's safe and reliable. I'll put that in quotes because it depends on what your interpretation is. There haven't been a lot of them, but the accidents that have happened have affected a lot of people. And that's where the negatives are. So the nuclear waste is a problem. There's thermal pollution, there's construction costs. Once a power plant has reached a certain level of degradation, it can't be used anymore. And so there is this decommissioning cost as well. It's also can be targets of terrorism. So if you want to affect a lot of people in an area, if you take out this power plant, it can affect a lot of people. And then the longevity of the power plants, they can't stay online forever. Again, I already mentioned that. So some policies in the past few years, which have been enacted. In 2010, there was a push for let's get some more nuclear power plants. However, it didn't get off the ground too much. I think there were a couple, again, power plants which were designed or proposed to be constructed. Yucca Mountain was identified as a repository for nuclear waste. An Energy Policy Act of 2005, again, we're giving incentives to more nuclear power. And in 2007, an Independence and Security Act of Energy promoted the American-built nuclear power plants in overseas markets. So maybe not in the U.S., but in other areas, nuclear is a viable option and is used much more extensively. And I think in France, it's up to 70% of their energy is used from nuclear power. So there are areas where it's used a lot. In New England in the U.S. uses quite a few nuclear power plants, but other areas where it's not used hardly at all. All right, that's nuclear power. The last thing we're going to talk about then is renewable energy. All right, renewable energy is mostly biomass. So this is like burning of wood, mostly. Hydropower using dams, wind. Solar is actually a really small slice of the pie. It's one that gets a lot of talk, but doesn't really have a lot of use. All right, but we'll start talking about solar. In order for solar power to work, you need a photovoltaic cell. Okay, and here's one here, which converts light energy into electrical energy. These are relatively cheap. The cost of these is decreasing over time, and the lifespan of each cell is about 20 years. So they aren't permanent in their use, but 20 years is a good amount of time for a product. It needs an inverter, so you have to have some interface between the cells and the electricity, and so that is where most of the cost is in solar power. There are a bunch of different types of solar power plants. You can concentrate the solar power using a solar trough, where it all kind of hits one point. Or you can have a dish engine system where you have an array of circular mirrors focusing on a receiver to transmit that energy to an engine. You also have, sometimes these fields, sometimes they rotate with the sun. Solar power is sometimes used for not necessarily electricity, but just for heating homes or heating water. So there are some water containers that you can put on your roof. That you see these a lot in like Central South America, and they are black, and that's how they get hot water, is just the sunlight beating on this black water tank warms up the water in there, and then that's the hot water. But you can also use it, the placement of windows and placement of other structures, the way your building faces can also take advantage of solar energy. All right, hydropower is the use of dams. Again, where you have the water pushing a turbo generator, converting that to electricity. The advantage is it doesn't use fossil fuels, it doesn't have nuclear waste. You can also use it for flood control and irrigation, so it's multiple use. Recreation and tourism, you make a lake, people can go water skiing on there. The disadvantage, though, is that it drowns everything upstream where you created this lake. Is no longer usable as land, so if there's any farmland or houses there, they have to be moved. It also prevents the migration of fish, which there is some solutions to. You have these installation of these fish ladders where they can swim up them. But it also makes a lake where there wasn't a lake, so that changes the ecosystem as well. You also have sediment buildup in the dams at the bottom of these lakes, and rather than in the deltas where they empty into the ocean. And a lot of water can, depending on how many times it's been dammed, can, by the time it gets to the ocean, be like completely dried up. So that happens to the Colorado River. We use that in multiple dams. By the time it empties into the Baja area in Mexico, it is almost nothing. I think in some areas it is. Some years it is nothing, and it's because we have used all the water before it gets there. Wind power. This is one that's increasingly more a viable option because with the use of more wind power plants, the cost as well has decreased, and the efficiency of being able to install these has increased as well. The wind power uses the wind, of course, to turn these turbines, which are connected to a turbo generator to produce electrical energy. The reliability and efficiency have improved, cost has decreased. However, it is an intermittent source, so some days it is not windy, and so it's not turning the turbines. It also kills birds and bats. Maybe a solution to that is to put them in the middle of the ocean where birds and bats don't fly as much. There are other things to consider as well, though. All right, another source is geothermal energy. So in areas which are close to lava or the magma where it's close to the ground, you could use that to heat water, and then that water could be used to turn a turbo generator and conduct electricity. These are not used very much. There are very few of them, and just because the practicality of it is hard to pull off. But it is a renewable energy source, not something you have to burn, and could be a very a clean way to get energy. You can also use thermal energy to cool and heat your house, depending on where you live. The ground generally stays the same temperature. So if you force air down into the ground in the summer, it should be cooler. And in the winter, it should be warmer if you're in a seasonal area. This is called a heat pump. All right, biomass energy. So you can just burn stuff and use that for energy. Wood is a limited resource, and it also produces pollutants into the air. Burning waste. There are some chemical, there are some countries in Europe which actually burn so much waste for powering their power plants that they have to ship in garbage from other countries. It does, however, produce methane, which is a greenhouse gas. All right, so finally, transportation is probably an area where we could use the most. I shouldn't say that, but there's a lot of, because pretty much every car that we use is fueled by gas. There's a lot of inefficiency there, a lot of use of fossil fuels, and so this needs a lot of work as far as what can be done to wean off of these fossil fuels and into renewable energy sources. So one solution is creating biofuels, where you grow a crop and then you ferment the products of that crop, and then you burn that alcohol. Originally, this was done with corn, but now there are many other plants that have been identified and are being developed to be used as biofuels as well. Biodiesels, so this is where you use oil and alcohol to burn as fuel, and this also can be used by byproducts of like cooking oil or grease from restaurants. You can use that and convert it into a biofuel, a biodiesel, and put it in your diesel engines. All right, one other one we're going to talk about is hydrogen cars. So you can condense hydrogen gas, combine it with oxygen, and it will form water and energy, and you can use that to power your car. The problem is hydrogen gas is hard to put in a form that is usable. You can, through a process called hydrolysis, using enzymes or passing the current through water, using solar energy, make hydrogen gas, but it's highly inefficient. And in fact, if you use solar energy just to make batteries, you would get a lot more out of it than trying to make hydrogen. But the advantage to it is it's clean. The only byproduct is water vapor. And so this would be it'd be interesting if we could find an efficient way to make hydrogen and use that to power our cars. It's also more efficient than combustion, but again, that is the actual reaction with oxygen and hydrogen. But getting hydrogen out of water is inefficient, so it takes more energy to get the hydrogen out than it does to get than the energy you get from making the water and combining it with oxygen. Okay, that's it for energy, and that'll be all 3 lectures that we cover on the exam.